Hi everyone, I'm Kevin Fong. I am a professor here in the Department of Science, Technology, Engineering and Public Policy. I am a doctor of medicine. I specialise in anaesthesia and I also fly with Kent, Surrey, Sussex Air Ambulance. We cover the whole of the southeast. So I started out life here studying physics, and I went to medical school, and for reasons I don't quite understand, I later on studied astronautics and space engineering, because that's what I wanted, that's what I had to do to try and get myself into the space program. We are going to try and do something very exciting in a few minutes' time. We're going to try and connect up with the space station, but before I do that, I'm going to introduce you to my very, very good friend, Dan Tani. Me and Dan got to know each other when I was working for NASA out in Houston. We're good buddies. Dan is a real former astronaut. He's flown 2 missions. He has done an International Space Station expedition. He's walked in space 5 times. He spent 130 days in space. So give it up for Dan Tani. He's got a better CV than me. So Dan, just before we get linked up here, sure, we're going to try and talk to our buddy Mike Barratt, who is also a doctor on Space Station. Not that I'm jealous at all. And we're going to try and get that. So this is Space Station we're trying to link up to, but it's not straightforward, is it, Dan?
Right. It's not straightforward. The Space Station goes around the world. It only takes 90 minutes to go all the way around the Earth. It's going 17,500 miles an hour. And so you've got to be pretty clever about how we're going to talk to them, and they're going to talk to us. And so there's a whole set of engineers that figure out how to do that.
And so, just tell me now, Space Station isn't just floating there in a fixed position, right, is it? Tell me how Space Station is moving and where it is and how high it is.
Yeah, I'm tracking it right now. There's a way to track it right now. So it's just now going northeast. It's going to go over Moscow, or Russia, and then into Asia. And so by the time we're talking to them, they're probably going to be I would think coming over the Pacific Ocean. But anyway, it almost doesn't matter exactly where it is, because it has satellites that it can see all the time. And so when they press the button, or when their images come off the space station, they'll get transmitted to a satellite that will then transmit, they'll bounce that signal back down onto Earth. So when we can talk to them, we're going to talk to them for, I think, 20 minutes or something. They're going to move a third of the way around the world in that 90 minutes. And so the magic of this connection between the thing and the satellite and back down to Earth, and then once it gets back down to Earth, it has to route to Houston, JSC, and then it's going to come to us. So it's got quite a journey that image and that voice has to take.
And you've spent a lot of time on Space Station. You have phoned me from space, I remember that very well. Tell me a bit about what our buddy Mike is going to be doing to get connected to us down here. What does it look like up there? Where is he going to talk to us from?
So he looked at his daily schedule, and at 13:15 or whenever we set this up, he has a time block and says, hey, talk to Kevin Fong and UCL. And so they have a very small procedure. They have to get ready. They have to set up the communication panel right. They have to get a camera set up all right. But we do many of these, and so it's common for us to be able to talk to students or children or schools or something exactly like this. So he's going to find a place. I assume find a place where he can float upside down, and show us that he's really in space. But I'm sure he's excited. He's excited to talk to you. You guys are really good friends. I'm friends with Mike too. But I'm sure he's looking forward to talking to us. I have other friends that are on the space station right now too. And I told them we're doing this thing. And if you see a couple fly by, I've told them to go fly through the camera, and then we'll say hi.
Yeah, so this is hilarious. So Dan has messaged his buddies on the space station, asked them to photobomb out, which I'm waiting to see. That'll be great. We are super lucky to get this. So my friend Mike Barratt I think he's commanding this expedition, right?
I believe that's correct.
He's mission commander, so he's busy and he's quite important in his...
I would say, Kevin, that most astronauts are given 2 opportunities to talk to their friends and groups down, and Mike has taken this chance to be one of his 2 opportunities. So it's important enough for him to want to support this.
So we are super lucky to be one of only 2 opportunities. Now, it is complicated, as you've heard Dan say. That vehicle is moving 17,000 miles an hour. That's how fast you have to move to stay in orbit at around 240, 250 nautical miles. and then it's got to beam on some satellites, these tracking and data relay satellites, the TDRS, and then it's going to come down to Earth somewhere in White Sands out on the west coast, right? White Sands.
Yeah, it's in New Mexico. Yep.
New Mexico, and then over to mission control in Johnson Space Center in Houston, Texas, and then from there it's going to beam to us by a good old-fashioned Zoom call, but it's coming a long way, so you'll see some delay when we're talking to Mike. We have been talking to mission control this morning. We think we're going to be good for this. It may not happen. If it doesn't, we'll have a whole different set of stuff. But we should be coming up.
I was promised tap dancing. Is that what
tap dancing? Yeah. I'm going to do a bit of comedy, and so we're coming up on acquisition of signal. At what time is?
They call them at
15:11. So 2 minutes. We're hoping to hook up to mission control at that point, and then we'll hopefully we'll see Mike first before we hear. Oh, here we are. So we won't be able to talk to him right now. We're just getting video. So this is good. This is work. There's Buddy Mike. And he can't see us, so he doesn't get any video to us, but he's going to get audio. But he probably can't hear us at the moment, and he's currently looking at stuff.
We're in the Japanese module here. It's called the Kibo module. It's the Japanese experiment module. And they have their own, this is called an airlock. So they can put, not a person, but they can put stuff in here and then close the hatch and then open the door that goes outside. So they can move stuff out to the into outer space through this thing called the airlock.
So this is very exciting. So this is the first stage for us. We've got video link. Audio comes down differently. So I'm hoping we get audio as well. The person you saw floating there was my friend Mike Barratt. It's funny, he looks a bit different to me to what I used to see on Earth. Because when you're in weightlessness, all the fluid that would normally be pooling in your legs floats up into your head, so you kind of get a puff face. I remember when Dan, you were up, and I would see him, and think, oh, Dan looks like he's had too many pies. But actually, it's just
the wrinkles go away. It's good because the wrinkles go away.
And tell me a bit about that, Dan. What it's like the first few days when you're in space and you're acclimatizing to those ships. Tell me about that.
Yeah, you go in and everything's weightless, and so you think you know what weightless looks like, or you think about, because you've seen astronauts before. But when you initially get into space and your weightless is floating around, you got to think, not only am I floating around in the cabin here, but my stomach is floating around in my body, and the food is floating around in my stomach. You got to think, oh, that's all a little different. And for the first day or so, your brain is like trying to figure out what is going on. Com check?
Com check. They're doing some com check, but yeah.
So your brain is pretty confused. And so for the first day or two, when I would eat something, because we eat on the regular schedule, you go to the bathroom on the regular schedule, all that stuff. So you're hungry, and so if I would eat something, it felt like the food was going into my throat and just sticking there. Now I know it doesn't. I know your body moves it all the way, but I had this feeling, unpleasant feeling, that all my food was sticking in my throat. And so your brain has to figure all that stuff out. But magically, by about the third day, you wake up and everything feels normal. Somehow your brain rearranged all the synapses to say, this is normal, this is fine, and you feel perfectly fine. So.
And some people describe the first couple of days feeling a bit sick when they're in space. Here he is.
Yep.
Hey,
Mike. We can't hear you.
We haven't got audio yet, but
no
he's
audio.
there. So this is Mike. So Mike's been up for a good
Mike. Got you loud. We have a loud and clear here in the auditorium.
5 by 5. Thank you, Mike.
Can you hear us? No. 1, 2, 3. 3, 2, 1. Com check. All right.
All right. So we've got that may have been a com check with Houston. He may not be linked up to us audio-wise yet, but he's just stowing some stuff, doing a bit of tidying, but I think possibly doesn't realize he's on camera yet, trying to tidy up the bedroom before visitors come.
So this is new. These are carabiners, and we didn't have them when I was up there. They're smart, but since everything's floating around, you need to control all your stuff. So like a pen, we have Velcro on pens because we would have to Velcro them to our wall or to our pants or even to our shirt. But I'm sure those are used for cameras or for other things because it's easy to lose things. And adding carabiners is smart. That's a smart addition.
So Mike Barratt Doctor of Medicine, was a flight surgeon at Johnson Space Center when I was there. This is, I think, his third mission.
Yeah,
third mission.
Yeah.
He's now just goofing around because I'm sure he doesn't think we're watching.
There we go.
And,
there it is. Yeah. There we go.
And that is really showing off. So Mike is a medical doctor. He specializes in internal medicine. And you might think he's upside down there, but there is no up and there is no down. To him, it's all the same.
Yeah, it doesn't feel any different being what we think of as upside down.
And so he's picking up the microphone.
Can't hear you. We're working on it. No, yeah, use the wireless.
So right now he's checking the comms with mission control, I am hoping, because there will be a delay. You'll see him speak, and then it has to go a long way, that signal, to get to us. So it doesn't come to us as fast as the video, I don't think. And he is telling me he's on the handheld there. And I have no audio.
He's talking to he's
talking to the desk.
Yeah.
Okay.
Right.
We're 6 minutes before we're up. That's pretty cool.
Yeah. Right.
So some of those modules are big enough that if you're a small astronaut, you can position the person in the middle, and they can't touch any of the sides, and they can't go anywhere.
They're stuck.
They're stuck. So you can't go anywhere. You can't swim in space.
Okay, comm check with the black mic in my right hand. 1, 2, 3, 4, 5.
And don't know if you can copy us here, Mike. That's
good
probably
comm
5 by 5. Good comm check.
We can hear him in London.
We can hear him on the handheld.
Sound check.
Yep.
You're getting a loud yes from the kids in the room here with me.
Can we ask you to just say another check, please? Can he hear you?
Check.
Mike, I'm checking comm this side, TX from London. Can you hear me? It's Kev.
And Dan.
And Dan.
Okay. Voice check. 1, 2, 3, 4, 5.
Yep.
You hear Kevin and Dan from here?
We have
So
good comm.
Mike, we've got good comm. Dan, Tani and I are waiting for you. I'm hoping you can hear me. So again, you have to remember, he's whizzing around the Earth at 17,500 miles an hour, going through a set of satellites, down to a ground station, through to mission control, and out to us. So this is not straightforward.
Well, that path is clear, so that's good. It's
That's
fantastic,
good.
so-
Well, he's not expecting to go on for 4 minutes, so maybe
really?
they'll
Okay.
hook us in 4.
Okay. The video's great. Video quality is great.
Video looks really good.
Yeah.
So it looks really cluttered up there.
Yeah,
doesn't
it's
it, Dan?
like most of the space station, we run experiments, and so all this stuff is there for a reason. I will notice so there's some tape, like we call it duct tape, or this is Kevin tape. You can't fly in space without a roll of tape. I don't know what most of the stuff is, but it's just various types of equipment for experiments, laptop computers. They have a robotic. They have a robotic arm, so that he's right near the robotic arm workstation. What else can you see? These are windows that you can see up, but they cover those. Oddly, they cover
Can you
those.
mute the mics in here, please?
Check.
So
Oh,
you
no.
might want to know.
Kevin, I think we need to. So you want us to keep the sound off here? Sorry, so I'm getting the mission control saying. Okay, so we need to be able to mute in between you speaking.
Okay.
Okay, so I think we'll need to be quiet in the room in between Kevin. Okay.
Voice check. Mike, it's Kev Fong, UCL. We are doing comm check with you. I'm hoping you're receiving me up there, buddy.
That's Kevin who exactly? No, just kidding. Professor Fong, my good friend Kevin, I hear you loud and clear.
Oh, wow. Hey, it is... You've got a room full of very excited people down here. Thank you so much for joining us here. I am here with Dan Tani, your buddy as well. He's just going to say some words here for you.
Just saying hi, Mike. You look great up there. Gem looks fantastic, and it's good to see you floating, and I'm very jealous.
Mike, how's the mission been so far?
Well, you should be. It's good to hear your voice, Dan. I'm sorry, say again, Kevin?
How's the mission been so far? How are you getting on up there? How long you been up?
Let's see, I think today is day 137, flight day. So, you know, the days are going by really fast. And we're up here for a standard 6-month tour, roughly 180 days. And I'm realizing as I'm counting these days down that there's a lot of stuff I still want to do and see. And there's sort of like an end of mission anxiety going on. So I could almost stay up here a lot longer and be happy. But it's been great. The mission has been very interesting. And it's been full of curveballs in some ways, and that's part of what makes spaceflight interesting. So we've had to adapt to a lot of new circumstances and some new house guests, which has been wonderful. And just the standard time of being up on this magnificent station has really been wonderful.
That's fantastic to hear, Mike. I'm going to rattle through some questions that our school children, we've got a room here, I know you can't see us, but we've got a room here full of students and school children that have been kind enough to give us some questions. I'm going to start off, we're going to rattle through them if that's okay with you. The first question is, and I know you're a medical doctor, Mike, but why does NASA like engineers so much for their astronauts?
Yeah, it's a good question. And you know, as you said, I'm not an engineer, but I've had to learn a lot of engineering since I've been up here. You know, if you look around me, I'm in the Japanese module right here, but the space flight that supports people involves complex systems that all have to come together and be integrated and work and talk to one another. And so we live in this artificial habitat of engineering systems. And so engineering solutions to some of the problems that keep astronauts alive and able to explore are really what we thrive on. So that engineering capability to develop, to run, to operate, to fix, to progress, to evolve these systems is really core to human spaceflight, just like it is to aviation. So, but engineering is a very broad field. You know, there's aerospace engineering, mechanical, electrical, and it can cover so many different things that are quite wonderful, even biomedical engineering.
That's fantastic. Thank you so much. So the next question really is a very basic one. We can see you in your cramped module there. That's the Japanese module. But how big is the space station and what does it feel like to be in it?
Well, actually, this is, I think, the largest single module that we have up here. The space station is actually quite large. It is like 35,000 cubic feet, and we sometimes compare that to a 5 or 6 bedroom house. But you can actually work in a module and not see someone else for a couple hours just because everybody can have 1 or 2 modules to themselves. And we can kind of get heads down in our work sometimes. So the station is actually quite large when you consider what it is. To put a point on it, when I came up here on STS-133 with one of my shipmates who was a submariner in a former life, and I flew him around the station and I asked him if this were a submarine, how many people would be on it? And he said like maybe 100 or something really outrageous. And we have a normal crew size of 7. So when you look at it that way, we have a lot of room. And of course, we can use all 3 dimensions of our space station, which makes a little bit of room even roomier. So when you can use 3 dimensions, you can invite a lot more people, sorry, to the galley table. So it's pretty big. It's definitely a really nice, comfortable space for 7 souls.
That's fantastic. Don't break anything while you're spinning around. It'll be expensive, I'm sure. So the next thing I want to know is, what does your schedule look like? When you wake up, what do you do? Are you busy? And when you go to sleep?
Yeah, we have a pretty regimented schedule. We have a wake up time of 6 a.m. every day. And by the way, we are on GMT. That universal time kind of splits the difference the best we can do with our international partners from Russia, Japan, the US, Canada, and whatnot. But we wake up at 6. We have a little bit of time to plan, to have breakfast, to think, and get ready for our day. That's restowing things from last night and pulling out tools that you're going to need. And then we go on about it. And because I get asked this a lot, I can show you what our schedule looks like. We live and die by these tablets now, and hopefully you can see that. But the timeline is this line that tells you what time it is now, and you're continually chasing that line throughout the day to get your tasks done as much as possible. And some of those are coordinated with the ground, some with other crew members, and it's really important to stay on time the best you can. And so sometimes we're busting chops pretty good to do that. And then, of course, in the evening when it's time to stop work, which can sometimes be kind of late, we have some downtime to eat and get ready for the next day. So the days are pretty regimented. A lot of us find that you can get by with a little less sleep up here than you do on the ground. You get kind of the same level of alertness. And that's been kind of good, but the days are busy, and because of that, they're very interesting. No two are alike.
That's great. Now, the next question is a really great one. What does the sun look like in the morning from the space station, and how do you keep a 24-hour day, bearing in mind you see a lot of sunsets and sunrises on the International Space Station?
It's a good question. So 16 sunrises and sunsets a day. But like a submarine, we kind of regulate it artificially. We regulate our days, our shift work, so to speak, and we're all in the same shift by, well, declaring it morning and turning on the lights in the space station. So we don't have big windows everywhere. It's pretty much artificial lighting. But one of the things I do is I get up in the morning and I will typically go open the windows of the cupola where we have our big bay windows that look down at the Earth and let the sun in if we're on that day pass. And you get a big blast of sunlight there for sure. But you are in total control over your exposure to the sun up here. And so that helps us regulate our sleep pretty well. In fact, we have tunable lights that are warmer in the evening when it's time to sleep and less so in the morning. They're very bright to wake you up in the morning. But when you want to go look at the Earth, you can do that anytime, and the sun goes with it.
And one of the students down here wants to know, did your attitude towards problems in life change when you look down at the Earth for the first time? We do hear people say that a lot, right? That things change when you look at the Earth from space. What was it like for you?
Yeah, the first look at the Earth comes at a very seminal moment for an astronaut, especially on your first flight, because typically that comes right after your rocket ride ascent. So for the last 9 minutes, you've been undergoing this acceleration that squeezes you down into your seat. And as soon as the engines cut off, you think, okay, we're in space, I'm alive. The engines survived and performed nicely. All of a sudden, the fluid rushes to your head. You feel like you're hanging upside down and your sense of balance goes totally whack. And your sense of motion control goes totally whack. And you're trying to look at your spaceship and make sure that the systems are healthy, and you're checking your crewmates to make sure that they're healthy. That's when you get your first look at the Earth. So it's not a clean experience. It's so many different sensory inputs that happen at once to coincide with that first look at the Earth. So I want to frame it that way. Having said that, that's the thing that lingers, that impression of seeing your home planet from space, how beautiful, how fragile it is. And I think most of us come away really with that cumulative experience of viewing the Earth daily up here, of this sense of how beautiful and how fragile the planet is, how much we need to take care of it, and how much we can get along with a lot less as far as resources than we do on the ground. So that's kind of my thinking about that first look at the Earth. Never forget it.
Lovely to hear that. And on the back of that romantic answer, I've got another question about life on the International Space Station, which, and I'm quoting it directly, is what happens to the toilet waste when the poo bag is full up?
It's funny, most people ask, how do you go to the bathroom? How do you fill the poo bag rather than what do you do with it afterwards? So that's an insightful question of somebody who wants to take the next step. It's actually a poo can. It's a very hard, very well sealed can, which has a lid bolted on top with 6 bolts. So we leave nothing to chance about letting anything out. And once that thing is totally full and compacted, we throw it in a trash bag. And then when we have a cargo ship of opportunity, which brings us cargo and then takes away all of our other trash, including the poo cans, we throw it all in there, we secure it down, and it burns up in the atmosphere. So in a way, our poo cans kind of get a Viking funeral at the end of their lifetime. No one's ever asked me that before.
No, it's a great question from a very insightful student. We're going to move on a little bit to training here. We're doing well, I think, on the clock. We're about 7-8 minutes into this link. Someone wants to know, what's the most interesting thing you saw or did while you were training to be an astronaut, Mike?
You know, it's a great question. I'll kind of make two global observations about training. And, you know, I've been an astronaut now for 24 years and change. The two biggest global things that have happened that really influence our training and our lives as astronauts are, you know, internationalization first. You know, we have the I in ISS is really international, and that includes working across cultural lines, system lines. Station is bilingual, so everybody has to have English and Russian proficiency. And learning how to work with one another and doing this very complex task in this very complex forum has had a huge impact on training. So it means a lot of international travel, language training, learning different systems. I mean, that's actually been pretty huge. And I think the other thing is commercialization. You know, we've got new entities now that provide more than just services or little bits of hardware widgets. They provide whole spacecraft. So when you look from an international standpoint, I flew the Russian Soyuz on my first flight. My third flight, I'm flying a commercial spacecraft. I flew the SpaceX Dragon to get up here. And all of those have implications in how we train and how we operate. So I think those are probably the two dominant things that I've seen changed in my very happy career as an astronaut because of these very interesting advances.
And related to that, someone wants to know, what was the hardest thing about astronaut training? And particularly, when did you feel like you might be closest to failing, if you ever felt like that?
Oh, yeah. So, you know, most of us are pretty well driven. I would kind of describe us as pro-space type A psychopaths, if you will. And as an astronaut, you kind of have to be master of many, many different skills, some of which are difficult to do. So that's spacewalking, robotics, all the systems that we have, scientific payloads. And it is really daunting to try to be a master of all of these. And over the years, you're going to have a bad day in some of these things that you do. One of the toughest physical things we do, physical and mental, is training for spacewalks. And yeah, I'll pull an example from training for this flight. My partner and I, Matt Dominic, were doing spacewalk training together. And it was my job to rescue him if he were to become incapacitated. And we have a time limit to do that. And I had a bit of a snarl with tethers, which I didn't recognize until late into that. So I got him into the airlock a few minutes after the allotted time. And you're physically exhausted, you're mentally exhausted, and you realize that you failed. And for us, that has deeper implications. It's kind of a self assessment, number one. And number two, I had to turn to my partner afterwards and said, you know, Matt, I'm sorry you're dead. We'll try to do better next time, because the implications are quite real. I will just tell you that I never failed at that again. I applied myself a lot more to it, maybe at the expense of some of the other things I was supposed to learn. But that's part and parcel to the diverse skills that we have to have in this job. And just like everywhere in life, everyone's going to have a bad day. I would say another attribute of being a successful astronaut is learning how to fail, learn from the mistake, pick up the pieces, and do better next time. And I think we all do that. That's a good question.
And good words. Thank you so much, Mike. And the final one on this section about training and being an astronaut, what's the best and worst thing about being an astronaut they want to know?
Well, the best thing, I think, is every astronaut is fueled by curiosity. I mean, that's one of the common factors that we have here. And the best thing is seeing new experiments. I mean, astronauts are happiest when they're learning new things. I think that's a truism. And so when we get to see results of experiments, or a spaceship that successfully flies after years of development that we had a hand in doing, I think that is absolutely the best ever for us, because everything is new. It's a movement that continues to evolve, and we're built on these periodic successes, whether it's experimental data or a new spaceship. For me, I guess the worst thing is just being away from family, international training, and being up here. And I think I'm like 16 days short of a year in space total, so that's another bit of time away from my family. But I think that would be my best and worst.
Thank you, Mike. So I'm going to move on to our home plate, which is a bit of space medicine here. And I want to ask, or at least one of our students wants to know, what are the challenges of being a doctor on the space station? And what do you do, for example, if you break a bone or something like that in space?
It's a good day for the doctors.
So we don't have interestingly, we don't have a requirement to have a doctor up here all the time. Now, it's interesting that we're almost 3 years into a period where we've had a continual presence of an MD on board, whether US or Canadian. And that really is nothing more than a coincidence. So when we have a doctor, it's great because it means that we can look for things and treat things very quickly without having to spend too much time talking to the ground acutely or read through a checklist. It really does help us. If we don't have a medical doctor assigned, then we will train a couple of crew members to a near paramedic level oriented to the problems that we see, and that helps us. But I would say if there's medical folks listening, the biggest challenge is really identifying medical problems before they happen. So really preventive medicine, which is kind of the beating heart of aerospace medicine as it is. But other challenges are identifying a problem and interpreting it in light of this new physiology we have, because we become extraterrestrials up here. Every system changes, and you have to interpret a new finding in light of reset cardiovascular control or shifting of anatomical organs. You're not going to find the right lower lobe of the liver 2 centimeters nicely below the right costal margin. It's just not there. It's somewhere else. It's higher. And then the other thing is, if you do identify a problem, is it a new problem? Is it an old problem? Is it environmentally induced? Is it internal pathological? Those are really big challenges. As far as breaking a bone, you think about what comes into the ED that leads to breaking bones. Well, it's falls and motor vehicle accidents and forces that we typically don't have up here. So that'll change with exploration on a planetary surface, but really we're more worried about internal things, whether they're induced by the environment, like some of our eye and brain changes, or they're just lurking in the background, like an appendix that's just waiting for the inopportune moment to get infected. So those are kind of some of them. I think Professor Fong knows very well. There's a community and a large knowledge base dedicated to exactly that issue. So go pursue.
Space sounds like a very dangerous place, Mike. If you need another doctor when you come down, tell Mission Control. I'm happy to go for you. I'm going to move on to the next question.
I'll put in a good word.
You better. The next question is how a simple one. How do you eat and drink in space? And what are the things that people don't really think about when they're thinking about your eating and drinking in space?
Well, the first thing is, because you're in zero gravity, everything has to be contained. So especially anything that's the fluids, for instance, you can't have an open cup of coffee. Everything has to be in a bag with a straw with a valve, and it's very important. You know, a rookie flyer, when they forget to close the valve and the coffee leaks out into a lovely brown ball before it liberates and splats onto something. So everything really has to be contained. The food that we eat has to be highly preserved. It has to have a long shelf life, so we can launch it well in advance and be sure that it's going to be up there and that it can last for a long period of time and keep its nutritional value as well as palatability. So we eat a lot of freeze-dried foods, foil-packed, military-type rations, canned foods, and they have to have some, what we call the stickiness factor, so that if you open a can of whatever, you don't want it to go flying all over the place. You want it to stick to the spoon that you have, or a nice, neat chunks that will adhere to your chopsticks when you pull them up. So highly preserved is one thing. We don't get a lot of fresh food up here, and long shelf life, and as convenient as possible, because as much as I love to cook, we don't have much time to prepare meals. You want it pretty much heat and eat, or rehydrate and eat. Now, having said that, I will say that it's kind of a golden age for eating up here, because we have so many international partners. Our menu is as diverse as it's ever been. So we have Russian food, Japanese food, Canadian, European, and that variety is huge. It keeps us wanting to eat, and frankly, I love to eat up here. So the food is very good. It'll be much more of a challenge when we're further away from Earth and low Earth orbit. things have to last longer and be even more compact.
And one of the questions here is what's the environment like up there, and particularly how hot is it up there? I've never really thought of that too much, but how comfortable is the temperature there? How hot is it? How do you manage that?
Well, I mean, we don't talk about the weather in the space station ever because it's 22 degrees centigrade. It was 22 degrees centigrade yesterday and last week and 2 months ago, and it'll be 22 degrees centigrade for the rest of the time I'm up here. We can set the temperature, but we kind of set it to the person with the lowest working thermostat. So that really doesn't change that much. It is very comfortable up here. So that is not an issue for us. It never changes. Our thermal control system keeps us pretty tightly regulated.
That is good to hear. And a couple of questions here about spacewalks. We're coming up 20 minutes. So, on which bit of the world are we over right now? Do you know? Dan's going to look it up here. I'm going to ask you this question while he's doing that. What is the oxygen concentration on the spacewalk? What oxygen concentration do you use on a spacewalk? Good question.
Yeah.
Yeah, well, so really quickly, the oxygen concentration in the station, it's sea level. It's 21% oxygen at 14.7 psi, 1 atmosphere. When we do a spacewalk, we have a suit that has a much lower pressure. It's about 4.3 psi, so a little less than a third of actually more like a quarter of what we would have in our sea level atmosphere. And to do that, to keep oxygen to a partial pressure that supports the person, the concentration has to be quite a bit higher. So it's 100% oxygen. It also makes it much simpler to have a single gas suit system. So we don't have to mix oxygen and nitrogen or just fly air, so to speak. We have to have a high concentration of oxygen at a low pressure, just like you need supplemental oxygen when you go to altitude. And so our spacesuits are 100% oxygen, 4.3 psi, 27 and something kilopascals or so.
And are you still looking forward to going on a spacewalk? I know you're due to go on one at some point. I think you enjoy those. Are you still scheduled to get out the airlock?
Well, that's an interesting question. I've been lucky enough to have 2 spacewalks in the Orlan suit, the Russian suit, many years ago. We've tried a couple times to get out the door here. We've had some technical issues that were unforeseen. Welcome to space flight. It throws you curveballs. And my partner, Tracy Dyson, and I were literally 30 minutes into our spacewalk and about to exit the airlock when we had an issue with one of the umbilicals. And the rest, as I say, is short-term engineering history where we recovered from that. And we're still troubleshooting our system. My hope is that we can still squeeze one out before we go, but we've had to defer that indefinitely while we're trying to figure out what's going on with our spacewalking system. It is something that we want to get back in line because you never know when a engineering problem will arise on the outside and we need to go out and change a critical hardware component out there. So it's something we always want to be ready to do. So it's I haven't been out the door, out of the airlock yet this flight. I'm not abandoning that hope, but it's one of those complicated things. You never know what's going to happen.
Yeah, well, I hope you do. I will be watching if and when you do. One of the other questions is, of course, we've heard that by 2030, they're supposed to be shutting down space station, and one of our students wants to know what comes after space station, what's going to happen, and what will they do with the old space station?
That's a great question. And, you know, we built the space station originally to have a life that ended, I believe, 2015 or so. And so we're well beyond the design lifetime of some of these modules. Come in. And they've actually performed quite marvelously beyond expectation anyway. So the fact that we're going to 2030 and we've grown so large is really quite amazing. Note the hair here. No, this is my partner, Sonny Williams, who I think Dan Tani knows very well. I'm going to finish that question and then let Sonny say hello, if that's okay. NASA is actually looking to have a commercial partner build and provide a successor to the International Space Station. And we would like to focus as an agency on more deep space exploration. It's something hard and places where we really have to keep pushing boundaries. And we'd like to turn over the management of the next generation station to a commercial entity if possible, And there's 2 or 3 contractors out there working really hard to come up with new designs, some that involve some of the core elements of this old bird, which is really becoming like a classic ship in a way, but still performing magnificently, and hybridized with newer technology and newer modules. So, I mean, it's an evolution that you expect. And it's another stepping stone, really, on humans becoming more and more present in low Earth orbit and beyond. I'm going to let Sunny say hello because it's a unique time. You know, we've got 3 spacecraft here that carry humans. We've got the Russian Soyuz at one end, which carried one of our American astronauts, Tracy Dyson. We got the Dragon, which carried one of our Russian cosmonauts, Alexander Grabyonkin. And we've got
the guests who have been staying a little long. You know, sometimes guests who stay more than like a week, you sort of want to kick them out. Hopefully we're not like that, but
no.
Butch Wilmore and myself, Sunny Williams, are here we came up on the Starliner spacecraft. June 5th, I think we launched and got here on the 6th. And we've sort of made ourselves at home here and loving every minute of being up here on the space station. So it's a little crowded, 9 people. But you don't even really notice it because everybody's doing different activities all over the space station. It's pretty big. So it's great to be here with Mike and his crew. They were very welcoming, and we're trying not to eat you out of house and home.
Yeah, they eat a lot, but they work like windmills. But you know, the root of your question is that when you look at station right now, how big it is, multiple docking ports, 3 different vehicles carrying people up here. And 1 cargo vehicle. We just got rid of a different cargo vehicle. We have another one coming up, the Cygnus. I mean, it's sort of like the Deep Space Nine of today, or maybe the Shallow Space 8, because we're only in low Earth orbit or whatever. But it's a thriving, vibrant station in the work that it does and the vehicles that come and go. So it's an insightful question, and we expect to see more of these in the future.
It's lovely. It's great to see you, Sunny. It's Kevin Fong here at UCL. I'm gonna hand the mic over to Dan Tani, who's here doing a selfie.
Yeah,
with the screen here, really
hold on, Sunny. I'm going to get a selfie here.
And I'm going to let him have a little chat with you. We're coming up to the end of our com window, but here's Dan.
Sonny, I just want to thank you. I mentioned we had this pass, and I wanted to see it because I got to see you. I didn't see you before you launched, actually. I saw Mike at JSC right before you guys launched, but didn't get to see you up properly. But anyway, I appreciate you dropping by and photobombing Mike's public affairs event. And anyway, it's terrific to see you. I can't wait to see you get back, and we can share some beverages and tell the stories. And right now, I'm giving you the Nemo wave.
Yeah, absolutely. You know,
It's our secret handshake here.
lots of stories, and I'm giving you the Nemo wave.
Okay, great.
So it's so great to see you, Mike. I think that we are coming up on the end of our com window, and I don't want to lose it while we're mid-sentence. Mate, it's so good to see. Oh. And that's spacewalk for you, perfect timing. So we're on the other side of the world right now. Wow, that was fantastic. That is not the first time I've spoken to Space Station, but it's the first time I've done it with video. That was a real treat. You don't get to do that too often. I have been working in this business for 30 years, and I've never got to do that before. So that was amazing. We are going to spend the rest of this session about 15 minutes or so, because we've still got an astronaut. We've got Dan. So we're going to take some questions from the audience here. And for those of you in Logan Hall, I'll repeat the questions as they're asked. And so if there are any questions, we're very happy to take them. Dan knows lots about space. Who wants to go first? Why don't we go here? Do you want to? You've forgotten. That's all right. That happens. Okay. You go. That's all right. That happens. How do you launch a rocket? Dan's going to tell us how you launch a rocket.
Well, that's very complicated. Rockets are big, very complicated machines. And the whole secret of a rocket, the whole reason you need a rocket is on the space station, they're going 17,500 miles an hour. And right here, we're going 0 miles an hour. And so you have to go fast so that you can get into orbit. And that's why rockets have big engines, and it's all exciting. there are companies that build these rockets, and they have seats, and you strap into them. And usually we sit in the rocket on our back, so that the speed that we get, the acceleration, it pushes us harder into our seat. Okay, so it's a little. In a couple years, when you go to high school, you'll understand better. But a rocket just throws out its propellant as fast as it possibly can, and when that happens, the rocket gets going faster and faster and faster and faster.
Oh, actually, that reminds me of a question I did have from somebody, which was, if you sneeze on the space station, do you end up going one way and the sneeze goes to the other?
We say MV equals MV, so it depends on how big it depends on how much whatever comes out of your nose weighs and how fast it's going. You'll get the opposite reaction.
Excellent, excellent. We're going to go there. Yes, go on. How come the galaxy looks so dark when? So why does the galaxy look so dark when we've got the sun in the middle of our solar system?
Well, galaxies that we can see are really, 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 really far away. I mean, farther away than you can even imagine. And if you were at that galaxy, it would have stars and everything would be bright, like, because we're very close to our sun. This stuff would be bright there. But we are so far away, that when we could see them at all, it looks like a little dim dot, but it's dark to us because we're so far away. But if you're in the galaxy, it could be bright. It would be like a bright sun day like today.
Good, sir.
Hi there. I was in the previous lecture. It was amazing. I'm actually a student here doing mechanical engineering.
Mechanical engineering.
And my question was, during the space shuttle missions, a lot of the candidates were either flight test engineers or flight test pilots. So how did you, having not been from that background, sell yourself through the application process and make yourself stand out?
I lied. No, you're right. They pull from pilots and test flight engineers, okay? Because they know those people already have a lot of the skills that they want astronauts to have. But they don't want just that population. They want doctors. They want scientists. They want general engineers. And so they want people to come in with a basic level of this kind of, we call it operational skill. So they looked at my background, and I had done some scuba diving. I've done some private pilot flying. Those are not necessary, but what they do is they show that I'm able to do and think at the same time, which is sometimes harder than you imagine. So, but as I pointed out in the previous session, that now spaceflight is changing a lot, and they're going to need, the space program, are going to need all sorts of expertise. And so, I talked about language specialists and fashion designers. If we're going to go to Mars, it's silly to bring 20 t-shirts to Mars, because that's just weight that you could use for something else. So once you wear your shirt for a month, I guarantee we're going to do something else with it. Maybe you eat it. Maybe you make it into a brick. Maybe you can somehow convert it into something. So we're going to need people that are specialists in all sorts of fields, not just flight engineers and pilots.
Young man in the corner there, go on.
Why did Jupiter's red spot shrink from the size of 3 Earths to the size of 1 Earth?
Oh, so this is quite a complex question. You're going to let me take that, yeah, thank you very much. The question was, why did Jupiter's spots shrink from the size of...
Jupiter's spots?
Yeah, from the size of 3 Earth diameters.
Yeah,
like the Great Red Storm, and that is an excellent question that I really wish I knew how to answer. so here's the thing, I'm going to go away and find out, and I'm going to get back to you on that one, because it's a long time. That's a fantastic question. Yeah. It's a really good question. And you know what? Jupiter's got it's not solid, it's like this very fluid set of clouds, and so they're able to mix and then fall apart, and sometimes these really quite strange things happen. And I guess that's what happened there. But, it's been about 30 years since I studied astrophysics, so I can't quite remember it. But I'll find out and I'll let you know. Okay. But a great question. That's brilliant. Yeah, go on. How do you make one of these? So I'm being shown what is that? Oh, it's a satellite. It's a satellite. Okay, I don't know what that is, so I don't know how to make it. Oh.
Saturn, it's the solar arrays?
Yeah, let me have a look. Let me have a look. What is
I
it?
can tell you what it is.
Okay.
I took a photo of what it was.
Okay. So we're at the moment, for those of you in Logan Hall who are wondering what is actually going on here, I'm looking at a postcard that's got a picture on it of a piece of space hardware that I actually can't identify. I have an astronaut working on this with me, so basically, there's no reason why I should know what this looks like. But
it's an experiment. It looks like it's some sort of experiment on a satellite.
We actually don't know how to make that either. We're really spoiling your expectations here, aren't we? We're going to go there and they're going to question there.
Oh, they're outside.
The actual people who made that are outside. Oh, well, there you go.
There you go.
Okay, cool.
Look for
Yeah,
the shirt.
ask them.
Don't tell them we didn't know.
Yeah, no. We know, but we didn't want to spoil it for you, yeah.
How does the work on the space station help to improve the daily lives of people down on Earth?
So space station is a laboratory, and it took 10 years to build it, but now we're finally able to open for business. And the business we get is it's a United States National Laboratory, and so investigators from all over the world go through NASA and try to get their experiments on space station. So, like research and development, some experiments we have, it's hard to say, oh yeah, that's how my life is going to improve because, so one of the experiments I did, which I thought was very interesting, is if you take, I'll say oil and vinegar, but if you take oil and water and you shake it up down here, you get, it's called an emulsion, and it'll look fine, and then over time, it'll separate like your salad dressing, and it's because gravity's pulling the heavier stuff, water, but without gravitational forces, it just stays like that in space, in low Earth orbit. Tell you what though, after months, the vinegar molecules and the oil molecules start to find each other and bond with each other, and then you get a very interesting mix. You get globules of water, you get globules of oil. What is that? What's going on there? So that was one of the experiments I did. I photographed this thing every day for months to see the change. And how does that change your life? Well, they're trying to figure out, they're trying to apply that to the magma of the Earth and what's going on inside the Earth, and how are the fluids that are inside the Earth coming together. What forces are there that we can't see because the gravitational forces overcome them? I guess my short answer is it's a laboratory, like a laboratory probably here at UCL or in many other places. It will change, it will better our lives. It's hard to draw the line from how does a flame work? Flame in space is really, really interesting that it's different. You light a candle here, the candle's nice and long. The reason it's nice and long, the flame is nice and long, is that it's hotter up here than it is over here, and so the buoyancy of the air, it wants to, air convects and it does that, and it makes the flame long. If you light a candle in space, you'll get a spherical, because there's no gravitational forces to pull air one way or another. So you get the spherical flame. How does that affect you? Well, it's hard to tell, but we're making people smarter about how flame works, how combustion works, and it's going to somehow come out in a better smoke detector for your house, or better flame retardants on airplanes, something like that. So long answer, but it's basic research and development.
Just there, yeah, go for it. Yeah.
How many times have I flown a rocket? I've launched on a rocket twice and landed on a rocket twice. Different rockets, interestingly. But I've launched and landed twice.
Yeah, go on. How fast can a rocket go?
Rockets to go to the space station, they end up going 17,500 miles an hour. Wow. So pretty fast.
And the ones that have to go to the moon go about 25,000 miles an hour. So it's pretty fast. Let's
She's
go.
had her hand up.
Oh yeah, go.
Really
go,
hard.
go,
You
go,
didn't
go.
light your hand.
Yeah,
She's
yeah.
really
Okay, yeah,
working
go,
hard.
go, go, go.
Yeah.
Why do rockets have cones on the top? What are you gesturing at me for? I'm not the one who's blown into space 3 times. So part of rocket has to do two jobs. It has to launch off the Earth, and when it's in space, it doesn't matter what shape it is, right? It can be any shape it wants.
Because there's no wind on it.
There's no wind on it in space. It's just a vacuum. But when it's going up through the atmosphere, it has to slip through the atmosphere, and right down near the surface of the Earth, the atmosphere is really thick. And so it has to be a good shape so that atmosphere can slip off of it. So you want to put a cone on it so that it has little resistance as possible as it's launching, and then you can use less fuel and you get more power. I hope that's right.
Good answer.
Yeah, go for it. How long has NASA been around for?
NASA was founded, I didn't know this was going to be hard questions. NASA was founded, I think, in 1961 or so. Before that, it was called NACA, the National Aeronautic Council Advisory, something like that. So there was a group of scientists, and then they formed NASA in 1961, and then they've been running our space program ever since.
Right. So we have time for only a couple more questions. We shall have yes. Go on. Yeah.
Tomorrow, I got my haircut tomorrow.
Okay.
Mars, so honestly, no. Here's the deal. Mars right now, so the moon takes about 3 days to get to, you get off, and then you come back anytime you want. So you work for a week, you work for a month, you work for a day, come back 3 days back. So manageable. Going to Mars, first of all, you can only go to Mars when you're close to Mars, and you're only close to Mars once every 25 months because it's the way the planets go around the sun, and there's a moment where Earth and Mars are kind of close together. That only happens every 26 months, 25, 26 months. Okay, so that's when you get a launch. Then it's going to take you about 10 months or so to get to Mars. Then you get off, and then now, because the planets are now out of place, you have to wait another 2 years before there's an opportunity to come back. So now you're looking at about a 4-year mission. Here's the other thing. You go to Mars, you're standing on Mars, you're high-fiving everybody, you're happy, and you look back at Earth. Where is Earth? You're so far away. You think about how hard it is to find Mars when you're standing here on Earth. Earth is going to be just as hard to find standing on Mars. And so you'll look at the sky and you go, no, is that the Earth? And it'll be hard to find it. Think of how psychologically hard it's going to be to know that that's your family, everybody you know, your life is, and you can hardly see it. I think there's big psychological issues about that separation, because right now on space station, they look down, I can see London go by, I can see Chicago come up. You don't feel far away, and on space station, you can be home in a couple hours if you had to be. So for me, psychologically, and where I am in my life, I wouldn't put my family through that, and I would have a hard time doing it. That said, there were thousands of people that were willing to sign up for a one-way trip to Mars. So there are people out there that want to do it. I'm just not one of them.
So we're at the end of time. We're going to overrun for just a few minutes to get 2 or 3 more questions in, if that's okay with everyone. So I'll take that question there.
So obviously you're very busy on the space station, but you obviously need to entertain yourself from time to time and also just relax. What games do you play, like James?
So the question for those of you in Logan Hall is you're obviously very busy in space. What games do you play to entertain yourself? Can you play Jenga? I think was the second question.
Jenga would be excellent, wouldn't it? Yeah, I think about that. On the space station, we're on a 5.5-day work schedule, meaning we are scheduled Monday through Friday, morning to night, and then half a day Saturday. And then we have a half a day Saturday and Sunday off, generally, unless there's something odd going on that week. And so there is some free time. And so I know it's up to astronaut preference, and whatever you can get on the computer, I'm sure that they have computer games. I didn't play any. We have a TV, big screen TV. Well, we used to call it a big screen TV. It's like 40 inches. And so you can, and people bring up their own hobbies. Some people actually, no kidding, have a specialist in making these types of baskets or some other hobby. So, I filled up all of my free time looking out the window, planning when I'm going to be over Chicago next, my hometown, so I can take a picture of it, looking through my list of friends to call. And so I kept myself very busy without without resorting, I didn't do any kind of games or any kind of, you know, we had a big, it's funny, DVD library, so we could watch a movie and spend some downtime. But during the week, I felt like I had no downtime, and on the weekend, I was either sleeping in or looking out the window. But they exist as long as the computer games comply with the security, blah, 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 and stuff like that. No Jenga, though. That's an excellent game.
We're going to try and take 3 more questions. I know you've had your hand up a lot. Yeah, go for it. Oh, what do stars look like in space? Well, I've never seen them in space, but luckily.
So it's a disappointing answer. They look exactly like they look from here because we're on the Earth. When we go to the space station, you know, like the space station or the shuttle, we're only this far off the planet. We're only 400 kilometers, 250 miles above the surface of the Earth. Stars are billions of miles away, millions and millions of miles away. And so you're not any really closer to the stars on the space station than you are here on Earth. What you do get is you get the benefit of a really black sky. And so if you go out on a clear night, it's usually like a winter, cold, clear night here, and you look up and there's no clouds. That happens about once a year, right? So no clouds. You'll see that black sky, that dark black sky. That's what it looks like from the space station.
And you had your hand up a long time.
No.
Yeah.
Go ahead.
Go ahead. I'll get you after
Yeah.
this. Go on. You go. Oh, how do you move when you're floating in space? Great question.
Awesome. That's awesome. Since we're floating around, our feet usually aren't touching anything, okay? And if you want to move, it takes a little bit of force. So you take your finger and you push over here, and you'll just start moving, right? And you'll move forever until you hit the other wall or hit somebody else, and now you can stop. Now he's moving. But you have to learn how to do that, and it's really fun. Yeah, what's your question?
So how much power do you need to fly a rocket?
How much power do you need to fly a rocket? Lots and lots and lots and lots. I'll let you get to high school before you figure out what the numbers are, but that's why rockets look so dramatic. Flames are coming out of them and everything, because it has to produce a lot of force to get me and my equipment going 17,500 miles an hour.
Quick one there.
How many light years is
The closest galaxy, how many light years? That is an excellent question, and I'm not sure I know the answer to that. The closest star system is about 4 light years, and that's Alpha Centauri. I think it's about 4 light years.
Something like that.
And galaxies-wise, these are huge distances we're talking about, because the galaxy that we live in is about 100 million light years across. And then space is mostly space, so it's mostly empty. So between galaxies, they are enormous distances. And so they will be, you know, millions of light years between. So I don't know exactly. I'll find out for you, don't worry.
Oh, you know
the answer.
Okay.
Okay, you know what the galaxy is. Okay, cool.
Uh-huh.
Well, look, we'll talk about it another time. At the back there. How do we think the increasing privatization of space is going to impact space travel, Dan? Me and Dan were talking about this over drinks last night.
So I work for a private space company now, and we're part of this privatization in space, and it's good and bad. Okay, so right now NASA has a system where if you're a professor and you want to fly an interesting thing, there's a process, and we can hopefully get that experiment in space, and it doesn't cost that professor anything. It's part of what the National Laboratory of International Space Station does. When you privatize, when a company now runs the space station, I think the process will be much simpler, because if you're a professor or somebody who has research that you want to do, that all you need to do is show up with enough money, and I'll get you on space. Okay, the process will be hopefully simpler, but unfortunately, if I'm a commercial space station provider, I need to make money. I need to cover my costs. And so there will be a path for subsidized research, but the primary method of getting space access is going to be money. So good and bad, I think it's going to be much more access if you have the money.
Okay, we are nearly at the end. We are going to take just 2 more questions. We're going to go there. Go on, yeah. Say again, please.
When?
When are we bringing democracy to the moon? Wow. Dan, that's your question. Yeah.
Well, so I'll answer it tangentially. There's an accord called the Artemis Accord, which is signed by, I don't know, 100 and something nations. And it's the rules that govern what's going to happen on the moon, when we get to the moon. Who controls it? Who owns it? Who can put spacecraft around it? Who can land spacecraft on it? What do the spacecraft have to do? What are the rules and regulations of exploring the moon? And so most of the countries in the world have signed that. And so we think we have an infrastructure of rules and regulations about that. I don't know if you call that democracy, but it's a way of coexisting on the moon. And so hopefully we can get 100% of the nations to agree to that, and then we'll have a complete agreement what happens when we get to the moon.
Great. Okay, and the last question. Go on, you two. Go on, tell me both of your questions.
How do you get gravity into a rocket?
Okay, how do you get gravity into a rocket, and what's your one?
And what was the first food in space?
The first
Best food.
First food in
No,
space. So how do you get gravity into a rocket, and what was the first food in space?
First or best? Best food.
First.
It's a big cake.
Okay, so gravity, you either have it or you don't have it. And so, so the reason gravity exists is any two things that have mass, that have weight, there's an attraction between them, and that's called gravity. And so if I stand close enough to Kevin, right, there's gravity between us. But honestly, no, you can't measure that because the Earth is so big. The gravity from the Earth is dominates. So gravity, you either have it or you don't. Food, the first food in space, we didn't know, when we first put people into space in the 60s, we didn't know anything about how bodies are going to act. And so one of the experiments on one of the first missions with people is to eat, because we just didn't have any idea. And so, so we had, I don't know what to equate it to nowadays, but we had these bars, kind of like a granola bar, sort of like a granola bar, and it was just an experiment. Can you eat it? Can you swallow? Will it go to where it's supposed to go? We laugh about it now because it's obvious it all works, but we didn't know that. So the first food in space was like an experiment. Can anybody eat at all?
And it wasn't very nice. They all
Probably wasn't very good.
The
Yeah,
food was awful.
Food's much better now.
It's much better now. It's really nice food now. And there is a way of getting something that feels like gravity in space if you spin things. So when I was at NASA, I worked on a program called the Artificial Gravity Program, and they were thinking, can you build a small, kind of like fairground ride and spin it really fast, about 40 times a minute, and generate something that looks like gravity? And you can do that, but you get really, really sick.
Yeah.
So, ladies and gentlemen, we've got to bring it to a close. Thank you so much for coming.
Thank you.
I hope you've enjoyed today. Thank you so much for being here. Enjoy the rest of the festival. It's been fantastic to see you all. Thanks for being here.
Thank you.